When we think about what keeps a modern hospital running, we usually picture the doctors and nurses. But behind every monitor, ventilator, and infusion pump is a clinical engineering department keeping that technology alive. This scorecard shows a harsh reality. 22% of adverse clinical events are directly attributed to medical device failure. Furthermore, relying on reactive, unplanned repairs costs 4.8 times more than a structured, proactive in-house maintenance program. This creates a tension for healthcare leadership. Do you spend upfront capital to build a dedicated repair infrastructure, or continue to outsource and accept a loss of operational autonomy? Moving toward an in-house model involves navigating rigid architectural requirements, utility constraints, and high-level regulatory standards. A poorly designed shop directly endangers patient care. It introduces the risk of cross-contamination or sudden failure of life support equipment on the floor. Building a facility correctly requires a specific, high-cost investment. The result is a workspace supporting long-term repair autonomy that meets rigorous healthcare safety audits. This floor plan outlines the mandatory physical layout of a clinical engineering shop. The non-negotiable foundation of this space is a strict dirty-to-clean workflow. Equipment coming off the floor goes straight into a dedicated decontamination room. This requires ground floor plumbing for deep sinks, spray nozzles, and a completely separate exhaust ventilation system. That infrastructure carries a significant cost, but it serves a critical function, stopping healthcare-associated infections right at the door before they can contaminate clean equipment. Moving into the main shop, industry standards mandate a strict minimum of 120 square feet per technician, plus dedicated space for part storage. This means a team of 4 technicians demands a footprint of over 400 square feet. This department cannot be tucked into a leftover closet. It requires a primary hospital placement. You also have to include an isolated mechanical zone. Heavy fabrication tools like bench grinders and drill presses require a separate space to keep metal shavings away from delicate electronic repairs. Compromising on this square footage results in overlapping clean and dirty zones, a direct violation of Joint Commission audit standards. This checklist breaks down the invisible utility infrastructure required at each bench, which goes far beyond standard office outlets. The first requirement is dual quad receptacles hardwired directly to the hospital's emergency generator network. While this increases electrical contracting costs, it is the only way to test life support equipment under realistic blackout conditions to ensure battery backups engage properly. For servicing respiratory or anesthesia equipment, you must include piped medical air, oxygen, and vacuum lines at the benches, alongside active scavenging systems to safely remove waste anesthetic gases. Finally, the workspace must be grounded with ESD-safe flooring and bench mats. This infrastructure provides a critical layer of protection for patient monitors, preventing the kind of silent, static-induced damage that can bypass a device's internal safeguards. These utility requirements represent a massive capital expenditure. They serve as a final defense for hypersensitive electronics, ensuring components don't fail after a device is returned to the patient's bedside. This comparison matrix illustrates the specific tools required for in-house board repair, starting with modern soldering solutions. Under the bench category, you'll need high-performance digital micro-soldering stations, like the Asian T3A or Hakko FX888D, which offer 25-second rapid heating and high thermal stability. These stations provide the exact thermal mass required for complex surface mount rework. The trade-off is that your technicians have to manage a library of specialized interchangeable tips. For triage, USB-C-powered smart soldering irons like the Pinasil V2 or FNRSI HS01 offer high portability for quick mobile fixes. While smart irons enable rapid wire repairs on the hospital floor, they lack the sustained heat and dual-channel capability needed for prolonged desktop rework. Beyond soldering, your baseline diagnostics revolve around digital multimeters to check voltage and oscilloscopes to visualize waveforms and detect timing issues. These diagnostic tools must be NIST traceable. This requires a commitment to recurring administrative recalibration schedules, so every measurement taken in the shop remains legally defensible. The objective at the bench level is precisely matching the thermal and diagnostic capabilities of your tools to the specific legal liability of the repair. This quadrant chart plots out biomedical analyzers, the most expensive and critical category of tools in the facility. Electrical safety analyzers sit in the top right quadrant. They are used daily to measure leakage currents and ground continuity. ESAs represent a massive capital expenditure for a tool that doesn't actually perform a repair. However, they are mandatory to verify compliance with IEC 62353 standards and protect patients from electric shock. You will also rely on specialized vital sign simulators and ultrasound phantoms to verify diagnostic outputs and therapeutic functions without using a human subject. These analyzers serve as the legal shield of the hospital. They provide the final, documented proof that a machine is clinically safe before it returns to a patient's room. This split-screen scenario outlines scaling your facility to your clinical load. For a 100-bed core shop, focus on environmental layout, ESD mats, HACO soldering stations, and NIST traceable multimeters. For a regional hub, invest in heavy infrastructure, lead-lined doors, NFPA 99 gas scavenging, and ISHN stations. That investment allows a facility to safely perform in-house repairs on high-dollar assets, like ventilators and complex radiology fleets. Your facility's architectural layout and bench-level tooling are the physical embodiment of patient safety. Design the shop with the exact precision of the life-saving devices you intend to repair.